This is number 2 off of the FRQ mock AP exam number 1. So let's read the problem here. Let y equals f of x be a particular solution to the differential equation dy dx equals 1 over xy with f of 1 equals 2. Part A says find the second derivative at the point 1, 2. We already have the first derivative, so we just have to make our way from first derivative to second derivative. So let's see what we can do. I'm going to rewrite this 1 over xy as xy quantity to the negative 1. That way I can just rely on chain rule and product rather than having to deal with quotient rule. So, but I recognize there's a need for chain rule here first. So outside derivative times inside derivative. So the outside function is negative 1 parentheses to the negative 2. And now we got to take care of the inside portion's derivative. But notice that these are two variables multiplied together, and there's a y involved, so we have to do product and implicit as well. So f prime g plus f g prime, f being the x and g being the y. So f prime, x becomes 1, the y stays, plus the x stays, and then g prime is y's derivative. The derivative for y is 1 dy dx. So now we have something in the that we can represent as the second derivative. I'm going to clean this up a little bit here. The y plus xy x dy dx can be up in the numerator along with the negative 1, and we can push this xy squared to the denominator. Now let's see if we can piece by piece convert these to be a numeric value. We know x and y can be replaced with 1 and 2. But we need to find a replacement for dy dx. So dy dx refers to this derivative formula. And if I want to find the derivative at 1, 2, I can take that dy dx, which is 1 over xy, replace x and y with 1 and 2, and I can make my substitution for dy dx to be 1/2. So x gets replaced with 1, y gets replaced with 2, so 1 times 2 squared. So now we have everything in terms of numeric values. Clean this up, we get negative 5/2 over 2 squared, which is same thing as negative 5/2 times 1/4, which is negative 5 over 8. Part B, write an equation for the line tangent to the graph of f at 1, 2 and use it to approximate f of 1.1. So this is a linear approximation. So linear approximation, we're going to first find the tangent line equation, and then once we have that tangent line equation, then we can put that decimal in to get that approximation. All right, so our order pair is 1, 2. Right, that's provided for us. The slope is based off of that dy dx equation that's given to us. So we can find the slope at 1, 2, which is 1/2. So we have our order pair, we have our slope, we put into point slope form, and then once we have our point slope form, then we put that decimal in for the x, and that will clean up to be 2.05. So that's the first part. The second part is saying, is the approximation greater or less than f of 1.1? Now, we're going to have to rely on the second derivative to help us out here. Now, the second derivative value we found from previous was negative 5/8, and so that is less than 0, obviously. And what we need to be able to connect with this number is the fact that a negative second derivative value means the graph is concave down. And visually, I want to show us what that looks like, right? You have a concave down graph. You have a line that is tangent to the curve. And so if the line is tangent to that point, then any point that sits on that tangent line equation, any linear approximation, is going to end up being an over approximation of the actual point on the graph. So if the graph is concave down, the tangent line will sit above the curve. Therefore, the approximation is greater than f of 1.1, resulting in resulting in the over approximation. And then likewise, if we have a graph that is concave up, and the tangent line is now going to have an opposite relationship here. Any point that sits on that tangent line equation is now going to be an under approximation. Right? So if the graph is concave down, our linear approximation is going to be an over approximation. If the graph is concave up, our linear line is going to be an under approximation. part C. Find the solution of the given differential equation. So we start with this differential equation. Let's go through our separation of variables. Cross multiply. I get xy dy is equal to dx. Not quite full separation, but it's easier to see what needs to come next. Our y and dy are in the right place. The dx is in the right place. Just this x is out of place. So we're going to divide that x over to the right side. So we have integral of y dy, integral of 1 over x dx. Power rule on this side, natural log on this side, and plus c. Don't forget that plus c shows up. So we can solve for c by plugging in that order pair, 1, 2. 1 goes in for x, 2 goes in for y. 4 over 2 is 2. 2 equals 0 plus c. C equals 2. Now that we have our c value, we're going to update our equation where we left off. And now we're going to try to get y by itself. So what I can do first, I need to get rid of that 2. So I'll multiply everything through by 2. And the only thing left to do now is to take the square root. So take the square root of both sides. There's a plus or minus that shows up, which indicates that these are two separate functions, and we need to decide which one is the one that we keep. Okay. And the way that we can tell is we look at the order pair, part C, sorry, and we look at the y value. Okay. Whatever the sign of the y value is going to guide whichever plus or minus to use. So in this case, our order pair has a y value of positive 2, so we want to choose the positive square root. All right, part D. Let g be a differentiable function such that g of x equals the inverse f of x. What is the value of g prime of 2? So we need to establish that relationship there between a function and its inverse, and also the relationship between their corresponding points or slopes at their corresponding points. So here's the general overview here. A function and its inverse will have slopes that are reciprocals of each other at their corresponding points. Okay. So what that means is if an order pair of 1, 2 exists on the f graph, then because the g function is the inverse, it must have this order pair of 2, 1. Now, the relationship is going to be at these points here. So at the slope of f, the slope of the graph at f of 1 is going to be related to the slope of the g graph at 2. So we know that the derivative of the slope of the f graph at 1 is going to be 1/2. All right, and that's based off of the derivative equation that we've been working through. Right, d over dx equals 1/2. So if the slope of the f graph is 1/2, then the slope of the g graph at 2, which is the corresponding point we've established, must be the reciprocal of that number. Okay, so just flip that number around, 1/2 becomes 2. Okay, just make sure that you're always keeping the same signs, that you're not changing the signs. And so if this was 3, this will become 1/3. If this was 2/3, this will be 3/2. Okay, and they're going to be at their corresponding points.